let's get to it. Let me fade out and fade back in, and then we'll begin our presentation. So we're gonna fade out, and and I lost the button. I seriously lost the button. There it is. Bam. Okay. So, hi everybody. I'm GatorStumps. We are going to be covering black holes today in class. I will be your teacher. I have no credentials whatsoever. I just happen to like the topic, and I vaguely might have it right. But I know it better than you do, and that's what matters. So now you will have a slightly better understanding of how this works. So, one of my mods was like, hey, how do black holes work? Because we've been playing Outer Wilds. In Outer Wilds, yes, I am repeating all this information. In Outer Wilds, there's a planet, Brittle Hollow, the one over there, the purplish one, has a moon circling it that's basically a lava ball, and chunks of lava are flying down and hitting the planet. And throughout the time that the game's going on, pieces of the planet are breaking, but they fall in, they don't explode. And the reason why they're falling in is there's actually a black hole that's been eating the inside of Brittle Hollow. And so they all fall into the black hole, and then elsewhere in the system they get sucked out the other end, because it's not just a black hole, it's a wormhole that spits it out over to the white hole at the other end of it. And then there's a white hole station. So by the end of the cycle, all the chunks are floating out over there. Half of Brittle Hollow's gone through the hole, and the other half is still barely floating around it. Anyways, that being said, Bears had asked me, hey, why doesn't that black hole just like consume everything? Like, I think that's inaccurate. I'm like, that's not quite how a black hole works. So to explain a black hole, this looks complicated, and it is, because this is three-dimensional, but it's cool. So I figured we'd start with this slide. So here's basically a depiction of a black hole. If you've seen the movie Interstellar, if you haven't seen the movie Interstellar, I highly recommend you watch it. You'll get a lot more information. You'll touch on a lot more topics, but it's not going to go into as much detail as I'm about to go into here. So the way a black hole works is pretty simple. So you have these four things. You have an accretion disk, the event horizon, the singularity, and the relativistic jet. I'm not going to talk too much about anything except for the event horizon and the singularity. So, but I will tell you, the accretion disk is when stuff is getting pulled in, it's spinning around it, kind of like the rings on Saturn, and so it will continue to circle around. The stuff that gets sucked in all the way, because everything's moving so fast around it, it creates a magnetic pole, essentially, and all that extra energy just shoots off the top, and that's called a relativistic jet. But let's simplify it a little bit more. That's a black hole. You got a circle, you got a dot, and that's really all the more you need. And the thing about a black hole is most black holes, the traditional concept of how a black hole forms is you have a sun that it starts out burning fuel, because suns start out as hydrogen and some helium. And as the hydrogen fuses together, every time hydrogen fuses together, like in a hydrogen bomb, it releases a huge amount of energy. And that's why we have the atomic bomb. That's why we have a nuclear power plant, actually, that's not why we have a nuclear power plant, because that's fission, not fusion. Different story. Anyways, but that's why we have the atomic bomb, is it's two things coming together, and the slamming into each other causes just this huge explosion. In the sun, what ends up happening is when space was first forming, there were all these particles just randomly floating, and naturally they all start to kind of clump together, like these two atoms clump, these two atoms clump, and as they continue to clump together, this cloud slowly ends up clumping into one big ball. And because it's all coming in from different angles, it's natural that that ball ends up spinning while it's clumping everything together. And once that ball gets enough stuff and it gets compressed enough, hey, Collywoggos, thanks for the subscription. 7-month streak, holy crap. But once all that crap like clumps together, all that hydrogen, and there's enough pressure, that much pressure creates heat, and once the heat is high enough, it ignites like fire, and that's how a star is born. And then as it's burning, it starts out by burning hydrogen, by fusing hydrogen together. So these hydrogen clump together and they become helium. So a good portion of the sun is actually helium. But as everything turns over into helium and you don't have any more hydrogen left, or very little hydrogen left, the sun's not hot enough to burn helium. It takes more heat to burn helium. So at that point in time, the sun starts to turn off because it doesn't have the power it needs to keep burning. So then what happens is once it cools off, it doesn't have that outward pressure. So then it starts to sink in on itself and it compresses more. And once it gets hot enough to ignite helium, then the sun reignites again and it burns helium. Then all that helium clumps together and it makes the next thing up on the table, and it keeps going up and up and up and up and up till a point where it's like burning carbon, and it's burning oxygen, and it's burning whatever it needs to every time it gets closer, and then ignites, and eventually it gets to a point where it hits iron. And iron is the first element on the periodic table that when you put two pieces together, it doesn't actually create heat, it actually costs heat. So it does the reverse of what a sun needs to do. At that point in time, once the sun's core starts to become that, it can't burn any more fuel, and it just sort of powers down. And so then the whole thing starts to collapse and collapse and collapse, and because iron is never going to create more energy and more heat, it's just going to keep compressing. And mathematically, when you have that much stuff of a full star, because let's remember that, like, here's the Earth, here's like Jupiter, and then like here's the sun. When you have that much heat or that much pressure, you hit a mathematical error where physically all the atoms should be so pressed together that they're almost occupying the same space. And then because that doesn't mathematically make sense, it doesn't fully explain how a supernova works. But what they've come to decide is that there's just a momentary like push where everything gets pushed past a boundary that makes mathematical sense, and the whole thing explodes in a supernova. And when everything explodes in a supernova, because of that complete pressure, you have two things that happens. One, you have the majority or a good portion of the sun blows its top and just like, as we've seen multiple times in this game. But what's left behind didn't get to explode out, it exploded in. And so that creates a black hole where you have this mathematical problem where stuff is so pressurized together, it doesn't have anything to do but perpetually go in on itself. So you have what you're seeing in this circle here, like ignore the word event horizon for this moment. Picture that black ball as the sun, and imagine taking everything that's the sun and pushing it down into a spot that is infinitely small. And that's what they call a singularity, because you're bringing it down to like one pinpoint. So, with that being said, what ends up happening, hang on, okay, so, but let me gather my thoughts, because I just derailed myself. But yeah, so you have all the sun, basically all that mass compressed into that one spot. Now here's where Bear's confusion was coming in, is he's like, it doesn't make sense, because my understanding and the misinformed myth is that a black hole will continue to suck everything in around it. And that's true, as long as there's stuff to suck in. But it's not like it's all going to perpetually pull everything in permanently. Because again, the sun only has so much power, right? I mean, the theory is the bigger thing is, the stronger its gravitational pull. That's why when you're on Earth, you weigh 200 pounds. But if you go on the moon, you weigh 1/8 of that, I think. Maybe that doesn't sound right. But you weigh a lot less on the moon. If you go on Jupiter, you become about as heavy as a truck. Actually, probably way heavier than that. But you become so heavy, your body crushes itself from the pressure of gravity pulling down on you. The sun is so massive that it keeps all the planets, including Pluto, way over there in orbit. But just because it became a black hole, it doesn't change the fact that inside that circle, that's the outer, what was the outer circle of the sun. So again, if we picture this whole circle to be the sun, even if all the mass is spread out in that spot, even if it's pushed all the way into the singularity, there's still the same amount of stuff, the same amount of mass in that single point. So it doesn't change the gravitational pull any. But just like anything else, if something falls into the sun, like my guy, over and over and over again, all that mass continues to build up. And over time, if you had a sun and something huge like a planet, I guess, was just to happen to conveniently come by and fall into the sun, now it would have the gravitational pull of the sun plus that planet. But because the sun is by itself, and it's not going to suck in Mercury because Mercury already has its orbit around it, just because the sun becomes a black hole, or even if the sun was a black hole, it's not going to change the fact that it doesn't have any more gravitational power. So then the big question becomes, how does a black hole become a what is a black hole exactly? Why is it black? Why is it scary? And all that kind of stuff. And it has to do with bending. Part of it has to do with bending light. So we're going to kind of go into a little bit of the explanation as to why black holes look weird like they do, because most people see this and they're like, I don't know what that is, but that's scary looking. Oh, Bear said he didn't get a notification that I went live, so he'll be here shortly. Anyways, while I wait for Bears, I'm going to explain a little bit more about the formation of the solar system. So, here you have an accretion disk, which is basically just more matter, more gas swirling around the black hole. The thing is, when the sun is first forming, it's all a cloud, just a big gas cloud with like some spots where the gas is clumped together, and it's getting more pressure, and it's becoming the planets as all that kind of junk comes together. When the sun finally ignites, the outward heat that propels it up, much like a hot air balloon, which causes, like, that heat causes the balloon to go up. Same thing. The moment the sun ignites, it creates a blast of energy that just pushes out all the excess gas, which is why there's nothing left in the solar system except for the sun and the biggest clumps of stuff, which would be the planets. So that all being said, once all that, because of the ignition and pushing all that gas out, when the sun finally dies and collapses in on itself, it doesn't have anything else to pull in, because all that gas, all that old gas and matter that it could have pulled in is totally gone and out of the way. Anyways, black holes have a fun effect that works like this, where it is called light bending. Einstein theorized a bunch of stuff, and I'm not going to get, my bad, I'm late. Bears, I'm going to give you a super quick crash course on what I just got done telling chat. So that's a black hole. And your original worst mod ever. So that's a black hole, theoretically. We're not going to talk much about the accretion disk, and we're not going to talk much about the relativistic disk, but we will talk about the event horizon and the singularity, because those, for the most simplistic form of a black hole, that's what it is. Because we'll just take this diagram right here. So what I was explaining was that when a sun first starts burning, it's all hydrogen, and the sun gets its heat by hydrogen slamming into each other and joining in. It's more about the learning experience than about modding. So the sun gets its heat by hydrogen slamming into each other, and then when they fuse together and become the next element up, which is helium, it releases energy, and that's why we see a burning sun. But over millions of years, what ends up happening is the hydrogen runs out or becomes so minimal that there isn't enough to produce enough heat and everything, because it's all been trapped into helium. So then the sun, because it can't burn anymore, because it's not hot enough to burn helium, it doesn't have the outward pressure of the heat, so it starts to collapse in on itself. And so once it collapses in on itself, oh, hey, Killing Riot, welcome back in. How are you tonight? Once the sun collapses in on itself, the pressure, because once you get pressure and you push something together, pressure creates heat. Once the pressure gets strong enough that it can ignite helium, then the sun reignites and expands back out. and starts burning helium. Once helium burns, helium, again, the heat from helium is caused by helium slamming into each other and fusing into the next thing. So we start to see that next element cool off, or the helium run out. Then the next element is there, and the sun contracts, and then that one ignites. So then what you end up doing is you keep getting this building cycle where, like, eventually the sun will be burning carbon until it runs out of carbon, and then the sun will collapse until it's hot enough to ignite oxygen, and then oxygen will burn, and then and it keeps doing this all the way up the periodic table until it hits iron. And iron is the first element on the table that when they fuse together, it doesn't actually create energy, it costs energy to fuse iron together. So it's the reverse of what a sun should do. So the moment a sun's core starts to become iron, it can't burn it anymore. And once it can't burn it anymore, the sun shuts off. And then once the sun shuts off, all of that pressure, all that stuff doesn't have any outward pressure, so it all starts to sink in, and it keeps sinking in. And when you're talking about a sun, it is so big that as it continues to sink in and in and in, it gets to a point mathematically where all of the atoms are basically pressed right up against each other. And if you know anything about the structure of an atom, the nucleus and the electron that's circling it is basically the distance of the sun and the eye of the universe. In fact, I think they use that concept to design the eye of the universe. I'm alright. How about you? Just got approved for a house. We're gonna get 4-bed. Wow, not for $660 a month. Nice, awesome. Congratulations, Riot. So, where did I leave off? Oh, so it gets to a point where all of the atoms are pressed close together, and you hit a mathematical problem where that much matter shouldn't be able to exist in that enclosed space. So one of two things have to happen. Either it has to somehow explode out, or it has to perpetually continue to sink into a single point, which is mathematically impossible. You can delete bears now too.
Can't delete odd messages.
It's fine. He's calling them out on it. Let me mute real quick. Okay. Anyways, so when you hit that mathematical problem of either all that mass of the sun either has to collapse in just perpetually over and over and over and over again till it gets down to a single dot, or even smaller than a single dot, where it becomes a singularity. It either has to mathematically do that, or it has to explode all the way out, and just to reverse all that pressure. And so what scientists have figured out from observation is it does both. So there comes a point where all that stuff is pushed together, and for a split second it all goes, and then even that little pressure out causes the sun to supernova. So it, like, I don't know what the percentage is. So let's just say half of the sun just blows off and explodes and obliterates everything. The other half didn't have anywhere to go. So it slammed inward, and it all collapsed into a black hole because it all collapsed into a single singularity. Because it's the only way that makes what doesn't make sense mathematically. Now, the part that Bears was having an issue with, and we'll go back to this map again, is that in Outer Wilds, Brittle Hollow is a planet that has basically, it's a hard shell, and in the center is a black hole, and pieces are breaking off and falling into the black hole. Hola, how are you doing? Found your GatorStump Twitch channel. Hey! How are you? Welcome in. I don't even know how I want to break down your name. Great job. I love that style. This should be 1 million views. Sun skimming black holes 101. I'm about to go do design and arts for your stream. Okay, you have fun with that. I'm going to continue to talk about black holes. We're doing a crash course on it. Although I don't know how long you've been hanging out. Take a look at the website address and my profile picture for Outer Wilds forever. I will do that at some later point in time, but I keep derailing myself because we're talking about black holes. But welcome in. Good to see you. we're going to explain black holes as we've been doing. If you haven't seen Interstellar, that's probably a really good starting point for black hole. Anyways, Bear's question was, why doesn't a black hole just keep growing and growing, expanding and eating everything? And the thing is, if you look at this picture, let's ignore the event horizon. Just take the circle of the sun, or take that big circle and say that's the mass of the sun. Even if you compress it all down to one singularity, that's still the mass of the sun. It doesn't change the fact that that big of a gravitational pull still exists in that single point. It doesn't matter if it's this big or this big. Pluto is still orbiting it and going around. Jupiter's still being pulled in and orbiting it. It doesn't change, like, outside of the fact that it blew half of its stuff off for a supernova, the black hole itself has a fixed amount of mass. And the only way it could bring in more matter is if other stuff happened to be getting pulled in. But when the sun first ignites, it blows away all the extra stuff around it and basically clears out the solar system, except for the largest clumps, which become the planets. So because of that, the sun can't, if the sun blew up into a black hole, that black hole is only going to have a certain amount of strength. And it's never going to get anything more unless stuff happens to fall into it, like asteroids or comets and stuff. But it would take forever. So the black hole in Brittle Hollow, assuming Brittle Hollow isn't breaking apart and constantly falling in, the black hole's not going to get a whole lot bigger than it already is. But it is interesting to think that the black hole in Brittle Hollow, despite how big it is, isn't strong enough to pull Brittle Hollow into itself. There are arguments as to why that could be, now that I start to think about it. But that's the gist of that. But I'm not going to go into the time-bendy stuff of black holes, but I do want to go into some of the other stuff because you need to understand how going into a black hole and coming out a white hole even works, because it does and it doesn't. So, and that first we got to explain why a black hole is black, and that has to do with light bending. So if you look at this picture, this is the Earth and this is the sun. And the sun, anytime they show a diagram to explain what a gravitational pull looks like, they always do it as like a gravity well. So the bigger the mass, the more pulls down on the fabric of space. And another thing that's important is we all have heard the classic term E equals mc squared, which is energy equals mass times the speed of light squared. And if you have energy on one side of the equal sign and you have mass on the other side of the equal sign, what you're saying is that anything that has mass can have energy and vice versa. And it has to, because if you have something that has energy but the energy is zero, then zero is going to equal zero, which means the mass has to be zero, and vice versa. The point that I'm coming to on this is that means that despite how fast light travels, light is energy, but it also has its own mass. Not a lot, and with how fast light travels, because it travels at 186,000 miles per second, if you have light traveling and it gets too close to a strong gravity, it'll pull it, just like just like anything else in orbit. And so if you have, in this diagram, I flipped it so it fit nicer, but in this diagram, if you look at the top, you have a star located at location A. But because the light is coming down past the sun, it's actually, that ray of light is being pulled by the sun's gravity, and it's curving around, and that's what we actually see. So even though for our point of view, it looks like we're seeing a star sitting at location B, we're actually seeing a star at location A. Which is kind of trippy, but we have visual proof of it. So this is a shot taken from, this is almost an exact representation of this. This is a shot taken from the Hubble telescope. It focused on a star. I don't think it was the sun. And you can see that blue ring around it. If you take that diagram with that one ray of light, and you create thousands upon thousands of rays of light, because a star is going to send light in every single possible direction. If you had light going around every side of that sun, and it was all being pulled back in, it would look like that. We would see this ring of light all the way around if it was perfectly behind the sun. And so in this image, there has to be a light source that is blue, that is almost directly behind that star. So it yeah, so back to this diagram, you would have a star sitting basically at location A. Actually, I have a better diagram, and it looks like this, but it looks really complicated. But now that I've talked about this, it should be a little simpler to understand. So that galaxy that they have in the top left corner, imagine that that's that blue light we were seeing. And then that bright light in the center is your heavy gravitation from a star. And so as the light from the galaxy is going by, it's being bent around the star. So we're getting it from multiple angles by the time it reaches Earth. So you take this simplistic concept, and then you give it that kind of bending around from every single possible way around that huge star, and then you get that. So the reason why I'm explaining this is it shows you that light can be pulled in. So I don't remember my next diagram. Make it more complicated for you now that you've kind of seen this part. This is another picture from the Hubble, and it's showing you that there are things that have so much gravity pull, much like the sun, or a cluster of stars that have so much gravity pull that, like the lensed quasars, that's what they call them. They call them they call them gravity lenses. So those four or five lensed quasars are actually one quasar where the light has gone out and been bent back in because it's been pulled back in. Same thing with those lensed galaxies that they have diagrammed. It's actually the exact same galaxy. If you turn it the right way, they will actually all three be the exact same image, which is just weird to think about. I need that one. So now we go to here. So when you have a black hole, like this is Saturn, let's theoretically say there's a black hole around Saturn. If you see the rings, they're all warped looking, and that is exactly because light is being pulled around it. So what it looks a lot like a big bubble. And so instead of like having a soap bubble floating in the air where you get all the image kind of warped and whatnot, that's because of reflection of light and mirroring and stuff like this. This is because the gravity of a black hole is so condensed that when light tries to go by it, it pulls it and bends it around. So, what do I got next? So here's why a black hole is black. A black hole has, actually I want to go back to real quick, we're going to go back to this image. A black hole has two main features. It has a singularity, which is the one pinpoint where all the mass is, and then you have the event horizon. And the event horizon is the outer threshold of this outer threshold of the black hole. That's what you're seeing. That's the surface. You can't see into the black hole. And that point where you can't see, that's the event horizon. So, where was I? So, let's take, for example, a ball. You throw a ball in the air. It goes up, like a diagram 1 and 2. It goes up, and it comes back down. You throw it higher, it goes higher, it comes back down. If you throw a ball hard enough, it will hit something called escape velocity. And escape velocity is how fast an item needs to be going away for gravity to not be able to pull it back in. So if you imagine, imagine standing on the Earth and shooting a rocket. If you can't get that rocket, obviously, if you can't get that rocket to go fast enough, it's going to get pulled back down. And here's the thing: is the same is true because light technically has mass, and so it does have a little bit of physical form. Technically, the same thing can happen to light. So when you have like this diagram, which is really fun to see, I should have used a different one, but this one's okay. But what does it say here? As the mass increases, so does the gravitational pull. If the gravitational pull is such that even light can't hit an escape velocity to break away, then a black hole is formed. And that's because the light will go up to a certain point before it's fully pulled back down. And that point where it can't go any further up before it gets pulled back down, if you imagine that in every single space all around the black hole, that's your event horizon. So theoretically, if you get past the event horizon, if there's light in there, you should be able to see it. But nobody's going to be able to see you, and you're never going to be able to break it because the fastest thing in existence is the speed of light. So, welcome in, Sid. We're explaining black holes, and I've restarted once, and I'm not going to restart again. But now that I've explained black holes, and I'm certain nobody understands what I've said because they're like, that's a lot of words, and it's Saturday night, we're going to go ahead and continue to talk about black holes. So, this image is cool. So, after everything I've said about bending light, you can see that there is a galaxy behind this black hole, but because it is bending light around it, you're seeing all that warped image, and it's actually the same stuff directly behind the black hole, but it's warped all the way around. The reason why you have a black circle dead center is because you're looking at that part of the black hole straight on. There isn't any light that's being bent into that spot, which goes back to one of the images that I can't recall. Not that one. Is it that one? Which comes back to this idea. If you look at the Earth, you can see where those orange lines where the light is being bent around the heavy object. There's that area there's the kind of like inside that banana shape. There's that stuff that there's no light being bent into it. Anything within that angular radius is going to look like that. It's just going to look like a big gaping black hole. And that's why and how we have black holes. So, to give you a demonstration, here's a cool video that NASA has that is a simulation of if you were sitting dead center. I don't have a good diagram. If you were sitting, let's see if I can balance this on my knee. If you were sitting dead center here, yeah, there we go, and you had one black hole here and one black hole here, and they were just, I can't do it, rotating around the whole time. This is what it would look like if you had two black holes circling you. So, yeah, that's cool. I'm just gonna let that one play. And at this point in time, do we have any questions? I guess the next question that Bears kind of brought up was, and I don't know if he realizes he asked this question, but it is important to answer the question. On a technicality, theoretically, if any amount of mass gets pushed together close enough, hard enough, it will create a black hole. But the only things in space that are in the universe that are known to be able to do that is a collapsing star, because the amount of pressure and the fact that it can't push back until it does a complete supernova. But in theory, if you slammed items hard enough together with enough pressure and enough mass, you could have mini black holes floating around, which would be cool. And so Brittle Hollow, however it formed, the inside of Brittle Hollow, if enough of the original part of Brittle Hollow just got like slammed together, it could theoretically make a black hole. Although it'd probably supernova first and blow apart the rest of the planet, but that doesn't matter. But because it's still just the inside of the planet pushed in on itself to be a small black hole, it's only going to have a small part of. There's a small game called A Slower Speed of Light, developed by students at MIT. Have you heard of it? I haven't, but I can imagine what they're talking about. Let me wrap up my thought here, Sid, and you can say what you want to say, but that kind of reminded me of something else. So, like I said, when the sun collapses, it's still the mass of the sun. It doesn't gain any more mass, which means it doesn't have any more gravitational power to just suck in the whole solar system. Same thing with the black hole in Brittle Hollow, is that as long as it's floating in the center of Brittle Hollow, it's not pulling any more than it normally would at any other point in time on the rest of Brittle Hollow. But again, you come down to the theory of, well, that big of a black hole would have enough pressure that it probably would rip the whole planet in. What? But it's a video game, so who's counting? So, back to what you were saying, Sid, fun thing about light. Oh, I'm going to start that video again because it's cool. A fun thing about light. Light, not only can you bend it, you can actually slow it down. And they've done it, where they've, light, if it goes through a medium, So light goes at 186,000 miles per hour. I don't know what the metric measurement is, but it goes 186,000 miles, not an hour, 186,000 miles per second. But if it goes through a medium like water, something thicker, it will get drag. And so they've done tests where they've taken light and basically reflected off of mirrors back and forth inside some sort of medium like water, and they've been able to slow it down enough to capture light moving. So it is possible. But like I said, we're not going to get into the whole theory about slowing down time because that gets really complicated. Actually, the fundamental principle of it's pretty cool and simple because you do the math and you're like, whoa, that's confusing. I get it. So Sid, when you get a chance, tell me about the slower speed of light. Otherwise, I will write myself a note. And I'm almost done. We got one more section of things to cover about black holes to answer the brittle hollow thing. A slower speed of light. Okay, so the last thing to cover is the concept of the wormhole. Now, that was weird. Okay, not necessarily. Oil has a higher refractive index than water, but not as dense as it. Okay, so maybe thicker is not the right word. But the point still remains, if you have a medium that is thicker than the vacuum of space, because that's where the speed of light is based off of, it's 186,000 miles per actually it's meters per second. Meters? Miles, one of the two. It's a ridiculously fast speed in the vacuum of space. But the moment you put it through an atmosphere, the moment you put it through water, you technically slow it down. But at that speed, who's counting? But here's where the complicated part becomes, is wormholes. Now, wormholes are theoretically formed from black holes. But the confusing thing is, if you take a black hole in its simple diagram, 3 times 10 for 3 times 10 to the 8th for general purposes. Okay, fair enough. I mean, like, I'm not trying to catch a light bus, so that will work just fine. But wormholes, if you take a black hole, the design I was explaining earlier, which I will bring up that image one last time, assuming I click the right buttons. If you take that basic diagram, that is based off the idea that the singularity is in the center and it's not doing anything weird. But we can't guarantee that they're going to do that. So hypothetically speaking, imagine you have a singularity that is basically circling a point. The singularity basically got shooken up and it's circling its own single point. So basically the singularity itself has a wobble. If it did, and it had an infinite pull for singularity, it'd basically be creating a whirlpool in space. And so the question becomes, if that whirlpool is wide enough, would it create basically a tunnel, a gateway through space? And then the next weird question becomes, where would it come out? And that's where we get into a lot of the Deep Space Nine, Babylon 5, Event Horizon, anything else where there's black hole teleportation. And so some people think that, and by saying some people think, I mean, like, there are a lot of different theories that all could possibly work. Either a black hole would end up spitting you out somewhere else in the galaxy. The black hole could spit you out in an alternate universe. These are all things that you kind of see in the end game for Outer Wilds. But here's the idea of the coolest thing I've ever seen for an explanation. Not even the coolest. I've seen this in multiple movies. Is they say, let's say you want to travel from here to here, but it's 3 light years away, which means it would take light itself 3 years to travel. By the time you got there, you'd be dead. However, if there was a way to fold space and then just punch a hole through, you would just be going through folded space and you'd be there instantly. And that's kind of the idea of a wormhole, and that's how a wormhole would form. So a better way to picture a wormhole would be to look at it like this. So you have space folded at one spot and at another, and it's joined together. And if you go on one side, you come out the other side. But the problem you're going to run into is the fact that when you go into the center of a wormhole, the amount of gravitational pressure of going into a wormhole from all sides of the wall as you're going through that thing should kill you. There's also the fact of if you ever touch the sides, you would technically be hitting a event horizon of the swirling thing, and the closer you get to the edge of a black hole, the slower time gets, and that's a whole different topic I'm not going to get into. But technically, the moment you touch an event horizon, your movement equals the speed of light, at which point, and it's not that it hits the speed of light, but it's the fact that time is basically zero, because gravity causes time to slow down. But because the singularity itself is exponential, because of it being an infinite singularity, when you hit the event horizon, that's the point in time stops. Not relative to you, but relative to everyone else. So the moment you touch the edge of a black hole and were to go in, nobody behind you watching would actually ever see you go into the black hole. You would be permanently frozen on the event horizon, because as far as can be seen, time is physically stopped at that point. It would look like a bug zapper, with just like permanently fixed bugs like slapped to it. So if you want to get technical, any movie where somebody's actually entered a black hole, that ain't gonna happen. The pressure would be too great and it would just crush them. Also, because it's exponential, they'd be shot down into the singularity so rapidly that you'd be stretched out into a line, which they call spaghettification. That is a word, which I'm very happy about. So that's my crash course on black holes and how they work. I'm going to, while we wrap up this and warm up for Outer Wilds, I'm going to turn this image back on because I love it. It's so cool. You can just do a YouTube search and do like black hole simulation and NASA, and I think it comes right up. So, again, disclaimers for anybody who's listened. My knowledge is me tapping my memory banks from like 12 years ago. I could have double majored in astrophysics, but I didn't. I got an English degree. Yep. So, wow, I really derailed myself. Like, well, that wasn't exactly the best choice, but I could have had a double major. So I've been fascinated. I love this stuff. Any sci-fi thing I can get on my hands on that actually is accurate in this fashion is cool. If you want to read stories about time distortion, you can either watch Interstellar, but the Ender Game series by Orson Scott Card, those are really cool. And they do a lot with time dilation, but yeah, again, so I'm amateur at best. I just like this stuff and I retain a lot of information. So I'm not guaranteeing that this is 100% accurate, but I don't think when you're talking about the basic theories, this is pretty close to how that works. Any questions? I'm going to slam my cup of coffee here right now